All right, it's 4 o'clock. Let's go and get started. All right, good evening, everyone, or I guess afternoon. Afternoon, everyone. How's everyone doing today? Doing good, doing good. Okay. All right, so today, all we're doing is we're just continuing on where we left off on Tuesday. So we were talking about motion capture and biomechanical kinematics. And so today we'll kind of get into the nitty gritty in terms of the details of how this happens. I brought a fairly detailed example with me. In fact, it's one of the problems from the next homework. So the next homework 5, is going to be posted sometime tonight. So I know homework 4, you guys are still working on it. That's due tonight. And so after that, homework 5 will be posted. And so you'll have that, that'll be out there. So homework 5 will be due in about 2.5 weeks. And so I believe the due date is going to be November 15th. And that's going to take us all the way up until the second midterm. So the second midterm exam is scheduled for November 17th, which is the last class session that we have before Thanksgiving break. And so, I'll give you guys an exam before Thanksgiving. I'll grade it over Thanksgiving break just so you guys don't have to worry about it. And then, we'll come back after Thanksgiving to start wrapping up the course. Okay. All right. And so, okay. So another announcement I want to make is that, make sure you guys are thinking about your final project. And so I've already gotten a few groups that have reached out to me and they said they formed a group and they know their topic. And so if you've already done that, then that's great. But if you haven't formed a group yet, I would definitely get on that. If you need help finding a group, then just let me know, shoot me an email. And then I can try to, play some matchmaker and get some groups together. Okay. But of course, you're welcome to use the Discord channel. I think maybe a couple people have joined recently, but I haven't approved the accounts on the Discord server, so I'll do that after class. And then just so you can get started, because there's quite a bit of research work that has to be done for the final project, and so you want to make sure that you're up to date. Okay. I apologize. My voice might be a little raspy today. I woke up with kind of a bad cough and sore throat, so that's why I kind of brought the mask in. And so if you can't hear me today, just let me know, and I'll be more than happy to repeat myself. It's a little bit hard to talk today. Okay, all right, and so that's all. That's it for my announcements. Are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off. And so last time, let me just scroll up a bit just to kind of remind you. Where we left off on Tuesday was we introduced this idea of inverse kinematics. And so the idea is that, we are going to assume from this point on that we have motion capture data. And so we've attached these motion capture markers onto the outside of a person's body. They've gone through their motions, and we have the positions of those markers with respect to time. Okay. But before we can actually make use of that data, the way that we are typically use this motion capture data is we use it to compute things like joint angles, joint angular velocities, and joint angular accelerations. And so there's a little bit of processing that we need to do in order to compute those from the raw motion capture data. And so that's what we're going to go over today. Because what we'll see is that, once we compute the joint angles and joint angular velocities, joint angular accelerations, we can use those in a dynamics analysis to compute things like muscle forces, joint reaction forces. So all the same things that we've done in the static analysis, but in dynamics. Okay? So this is kind of the pre-step that we need in order to do that. Okay. And so the way that we're going to accomplish that is that we're going to use the motion capture data to define basically a local set of coordinates or a local reference frame for each of the body segments. Okay? And the idea is that if we can track these body segment coordinate frames or reference frames with respect to time, then all we have to do is just kind of observe and measure the differences in orientation between these reference frames. And that's going to give us the joint kinematics that we need for the dynamics analysis. Okay? And so that's what kind of today is going to be all about. Okay? Okay, so it's going to be about inverse kinematics. Okay. So once again, the goal, take motion capture data. So the idea is that we're going to take the motion capture data we have and use that to compute the joint angles, with respect to time. All right, so to do this, the setup for it is a little bit sophisticated. So we're going to go over it in a second. So kind of the general practice for doing this is that for each body segment, we're actually going to define two reference frames. Okay. And both of these are going to be local to the same segment. So each segment, so let's say that your lower arm, your upper arm are going to have two coordinate frames associated with them. Okay. And you might be asking, why do we need two? And so, because if we look back at what we talked about last time, it looks like we only need one reference frame, right? So we only need one set of XY coordinates or XYZ in 3D per body segment to define the angles. But what you'll see is that the reason we do two is more practical than anything. Okay? All right, so let's define these two reference frames and then let's talk about what they're used for. All right, so the first reference frame that we'll talk about is called the anatomical reference frame. Sometimes you'll see it shortened as the ACS, excuse me. ACS stands for anatomical coordinate system. So coordinate system, reference frame, those terms are interchangeable, so they mean the same thing. Okay. And so the anatomical reference frame is based on the underlying skeletal geometry. Okay. Because each body segment in your body has at least one bone that's associated with it. Okay. And the reason we like to fix a reference frame here is because the bone is probably the most rigid part of the body segment. Okay. And if you look up actually the textbook definition of joint angles, it's specifically referring to the angle between adjacent bones. Okay. And so what the anatomical reference frame is used for is these give us our joint angle measurements. So ultimately, the ACS is what we want, because we want to be able to say, this reference frame is attached to the underlying bone. And then if we measure the anatomical reference frame of the lower arm versus the anatomical reference frame of the upper arm, the difference in orientation between those two is going to give us the joint angles exactly. Okay. So ideally, if we were to have just one reference frame for each body segment, it would be the ACS, because this gives us the joint angles that we need. Okay. And so in a perfect world, without any practical difficulties, the ACS would be all we need. Okay. So, if I were to draw an example here from the arm, it might look something like this. And so if we were to take a skeleton, it's appropriate. Halloween is next Monday. Okay. So let's say this is the humerus, which is the bone in your upper arm. Here you have your elbow joint. Okay. And then down in your lower arm, you have two bones. You have the radius and the ulna. They're kind of like in parallel like this. Here you have your wrist, and then you have your hand bones, which I'm not going to draw. Okay. But I'm labeling all of these in case, you know, my poor drawing skills don't make it clear. Okay. All right. So those are the bones that are in your arm. And so ideally what can happen is that if you have your anatomical reference frame, you know, you would have one set of coordinates that maybe is defined like this. Okay. Where maybe the x-axis goes right down the barrel of the humerus, and then the y-axis is perpendicular to it. And then you have another reference frame that maybe splits the difference between the two, the radius and the ulna, or maybe it is attached to the radius and the ulna. Maybe we'll call this x2, y2, and the first one we call x1, y1. Okay. All right. So that's what an anatomical reference frame would be like. It would be attached to, you know, or the reference point or the origin of these reference frames would be on the bones on the interior. Okay. And the reason we like to do this is because the bones are rigid. They're a lot more rigid than the muscle, which are soft tissue, than your skin or the fat around the bones. And so, you know, this would give us the most reliable and consistent kind of measurements of, you know, the orientation of those body segments. Okay. Okay. And the way that we obtain the anatomical reference frame, or ACS, is that we put our motion trackers, kind of on specific landmarks on the outside of the body. So usually, you know, if you kind of feel around your arm, you know, there's parts of your arm where the bone kind of sticks out. And so if you look right at your elbow, you can see that there's quite a, you know, hard bone right there. And then there's parts of your shoulder, which kind of line up pretty well too, where the muscle is actually pretty thin. Okay. And so you can actually get a pretty good estimate or a pretty good approximation for the ACS if you put the markers on what I call kind of boning landmarks, or kind of the key points on the body segment. Okay. Okay. And so places where the bone either comes very close to the skin that aren't going to move that much. And so you can put the markers in those areas. And if you kind of triangulate it, you know, which I'll kind of show you how to do that in a bit, then you can get a good estimate for these anatomical coordinate systems. Okay. Okay. So that's kind of the first type of reference frame that we use in inverse kinematics. Ideally, if in a perfect world, this is all that we would need, but you can see, we'll talk about in a second, there's some practical difficulties with this, where you need to kind of pull in a second reference frame. All right, any questions on ACS here? Okay. Okay, so that's the anatomical reference frame. And so it would be great if you can use that. And sometimes you can, depending on the part of the body. But what happens more often than not is that if you put the motion trackers on those boning landmarks, a lot of times they're in places that get covered up as the person goes through their motion. And so, in other words, you're not going to be able to track those markers well all throughout an entire, you know, complex motion. Okay. And so what ends up happening is that you have to have a kind of a second set of markers that you can place that are much more easy to track than the anatomical ones. And we call that the tracking reference frame. Sometimes this is shortened to TCS. All right, so the idea with the tracking reference frame is that you put the motion trackers in locations that are going to be easily tracked by the camera system in your setup. Okay. And so if you have knowledge of, where, let's say that you're working with a dozen cameras, and so if you have knowledge of where the dozen cameras are going to be, and you want to track the motion of, say, the arm, you would put the markers in such a way where, even if the person's kind of doing jumping jacks or, doing a baseball pitch or whatever, all the trackers will always be tracked by at least a good set of the cameras. So, and so they're not going to be obscured by the motion. Okay, so that's good. But the problem with the TCS is that because you have to put them in places that are usually determined by where your cameras are, they're not going to be lined up with the underlying bones underneath the body. Okay. Okay. And so you can't really compute body or joint angles from these because they're going to be kind of oriented in kind of a strange way. Okay. Especially if you're going kind of segment to segment. And so if you look at the TCS of, let's say the lower arm and the TCS of the upper arm, they're going to be pointed in somewhat random directions depending on where your cameras are. And so it's really hard to determine, what the joint angle is going to be because there might already be some kind of passive passive rotation in between them. Okay. So as an example, let's look and see what the two reference systems would look like for, like, say, the leg. So let me go ahead and draw the upper leg and the lower leg. Okay. I'm not going to draw the feet because feet are weird. Okay. So let's kind of define where the anatomical reference frame would be. So the anatomical reference frame, might look something like this. And so we're going to make use of the fact that the knee is a relatively bony joint. And so we'll put trackers maybe on the front of the kneecap, maybe the back of the knee, and maybe right on your hip, kind of where your hip bone kind of comes out. Okay? And so these are all locations where the bone comes fairly close to the skin. And so you can put markers on there and you can triangulate to get the system from there. And so in red here, I'm going to draw the anatomical reference frame. And then we can do the same thing, for the lower leg too. And so for the lower leg, two nice bony landmarks are, if you kind of look and feel around your foot, you have kind of a bone that kind of sticks out. That's the tibia, and on the kind of the inside of your ankle, and then on the outside of your ankle, you have the fibula. Okay, and so you can put markers there as well to kind of mark the anatomical reference frame of the lower leg. Okay. So remember, for the anatomical reference frame, the markers markers are placed on the boning landmarks of the segment. Okay. From these, let's say that we draw a coordinate axis, and so let's say that from these we're able to make coordinate axes that look like this. Okay, so maybe this is y1, x1, and then from these we can triangulate x1, x2, y2. Okay. And so because these coordinate axes are kind of defined down the length of the bones, then their relative orientations will give us the body angles exactly. So that works out. Okay. Okay. And so the problem with this, and so let's take the tracker on the back of the knee, for example, right? And so the tracker that's on the back of your knee, is going to be covered up a lot, because let's say that you're running, you're jogging, you're flexing your knee a lot, and so every time you flex your knee, it's going to cover up this marker back here, right? And so as soon as you lose kind of just one of the markers, then you kind of lose the entire definition of the entire reference frame. You kind of need to see all three in order to fully define the coordinate system. Okay. And so here the back of the knee is in kind of an inconvenient location, because you're going to lose track of it pretty often during the motion. Okay. And so to alleviate this, what you can do is you can draw you can put down other markers onto the to the leg, okay? And you're going to put them in locations that are kind of easier to see. And so, your thigh is kind of this big, kind of wide portion of the body. Okay? And so let's say we put 3 markers right here. Okay? And so let's say that, most of the cameras that we have are going to be in front of us. And so any markers that we put kind of on the front of the thigh here are going to be picked up by those cameras fairly often. Okay. And then for the lower leg, let's say that we put 3 markers that maybe look something like this. Just remember, the idea with the tracking reference frame is that they're an easy to track location. So you can see all 3 markers basically all the time. Okay? And that's good, because remember, you're going to need all 3 markers to define their coordinate system. And so let's say that we have a coordinate system like this, x2, maybe y2, maybe we have one like this. Oh, sorry, top one will be x1, y1. And I'll give a prime for that one to indicate that they're tracking reference frame. Okay. Right, so you can see that they're kind of going in different directions, and so they're not really lined up with the bones, and so you can't really use these to track the joint angles. All right, so this is kind of a relatively simple case, but I think hopefully this kind of illustrates the need for both and kind of what role both of them play. Okay. All right, any questions on this so far? Yeah.
Wouldn't this be somewhat connected because of muscle motion?
Yeah, no, that's a good point, and for the tracking reference frame too, you want to put it in locations that's not going to ripple as much for the muscles too. So yeah, there's a lot of kind of finer details and kind of where the best place to put these markers on, where they're not going to move with the muscle, they're not going to kind of jiggle with any fat and stuff like that too. So yeah, so with the tracking reference frame, you want to put them in easy to see locations, and locations where they're not going to move as much too. And sometimes you can double count too. And so for this example here, if we put a marker on the front of the knee, that one's probably going to be tracked really easily, and you can use it for the anatomical one too. So you can kind of double count some markers for both if they're in a really good location. Yeah, because the boning landmarks are kind of places where it's not going to move all that much too. And so yeah, and so if the boning landmark is in a good location, then you can use it for multiple other reference frames. Any other questions on this? Okay. All right, and so, those are the two reference frames that get defined a lot. And so that's why, when you see someone in mocap suit, they have like dozens of trackers on them. Okay, so more than 3 per segment. The next question you might ask is, how do we actually, compare these two? Because, we say that the anatomical one is needed to define the joint angles, but we don't see them all the time. Then how do we kind of relate the tracking reference frame to the anatomical one? Because that relationship is going to be needed to actually take data from the tracking reference frame to joint angles. And so what happens at the beginning of every motion capture study is that you have to do a little bit of calibration. Okay. And so what you're going to ask the patient to do, or what you're going to ask your subject to do, is at the very beginning, you're going to have them stand in a position where they can see both the anatomical markers and the tracking markers at the same time. Okay. And then the idea is that, if you can see both at the same time, you can see what their relative orientation is relative to each other. Okay. Right, so there's always going to be a calibrating step to make sure that all those motion factors can be referred to each other. Okay, and then once you achieve that, then what you can define is something called a transformation matrix that mathematically takes you from the tracking reference frame to the anatomical one, and vice versa. And so the transformation matrix is it's a square matrix, and so it's a linear algebra thing that you can multiply the coordinates in one reference frame to get the coordinates in another reference frame. So we'll go over what that is in a second, but that's basically what's done. So in a calibration step, you go you try to view both systems, and you kind of form this transformation matrix. And that transformation matrix is going to be kind of key to kind of a lot of the analysis that we do. Okay. Okay, so let's define what the transformation matrix is. All right, and so let's kind of define what they are in 2D, and then we'll kind of extend their definition in 3D. Okay, and so in 2D, we only have just a single angle, right? And so if we have two reference frames, the only thing that kind of differentiates the two is just an angle of rotation. Okay. So let me go ahead and find that. And so let's say that we're starting with kind of the standard X, Y. Okay, so X being horizontal, Y being vertical. Okay. If we were to change this or change the orientation of these, really we only have kind of one option here, is to kind of rotate it by an angle theta. Okay. We'll call this X prime, Y prime. what's interesting is that you can take two coordinate systems like this. If we define a point in space P, okay, and so that P is going to be the same in both coordinate systems, or its locations, physical location is going to be the same. But if we try to describe the location of P in the first reference frame versus the second reference frame, it's going to have a different coordinates or a different description because the coordinate systems are different. Okay. It's the same point P, and so it's not moving in between the two coordinate systems. So just because the coordinate systems are rotating, the physical locations of things in space are not changing, but it's just the way that we describe it, is different, right? So it's just like, if I were to describe this this Elmo projector here, right? So compared to my location here, it's only like, I don't know, like a few feet away from me. But if you compare it to, maybe someone sitting in the back, it's going to be a lot further away from them. The Elmo projector isn't moving, it's still in the same spot. It's just that its location relative to different points of view or different perspectives are going to be different. Okay. And so the same thing is true for rotated coordinates as well. And so, depending on which coordinate system that we're in, how we describe the locations of things it's going to be different. Okay. But there should be some kind of relationship between the two. Okay. And so just because our descriptions are different, if we have some knowledge of how the two coordinate systems are related to each other, a la the angle of rotation, then we can come up with a relationship in terms of the different ways we can describe location. Okay. Okay. All right, so that's the idea for the transformation matrix. So the transformation matrix basically says that, if we have the point P and we describe its location in the XY coordinates, and so we have PX, PY, okay. Let's say that this distance here is PX, this distance here is PY, okay. What we want to find is a relationship between how we can describe P in terms of the new coordinate system, in this case, X prime and Y prime. And so if we were to say that, this distance right here, this is P Y prime, this distance here, this is P X prime, okay? Okay, so it's the same P, but its location is being described in two different coordinates, okay? We should be able to form some kind of relationship here where, what symbol did I get? Okay. And so where this R right here is like some kind of transformation matrix. And so if we take the coordinates in the rotated coordinate system, we multiply it by a transformation matrix, that should give us the old coordinates or the coordinates in the original system. Okay. So this transformation matrix kind of serves as a link. It serves as a link between the two coordinate systems. Okay. And what you'll see is that we can derive this transformation matrix, or we can get its values just based on the angle rotation. Okay. Okay. All right, so let's get into some of the math associated with this. Okay. And so I'm actually going to use this example here. So what I'm going to do is I'm going to use I prime and j prime to represent unit vectors in the rotated coordinates. Okay. For I and j, no prime. I and j are going to be unit vectors in the original coordinate system. Okay. Okay, so let's do this. And so let me go ahead and draw I prime here. And so I prime, we know, is kind of rotated up and to the right. Okay. If I were to kind of finish this triangle here, we go ahead and draw a right triangle, where the angle on this triangle is theta. Okay. Remember, theta here is the amount that we're rotating the coordinate system. What we can do is we can find the lengths of each of these sides of the triangle. Okay. Okay. And what's significant about this, and the reason I kind of drew the triangle like this, is that the horizontal, kind of the bottom edge of the triangle, this is in the same direction as I, the I vector, not, I without any mark on it. Whereas the vertical side, because this is going straight up and down, this is in the same direction as J.
Sorry, in the magenta, is that supposed to be I prime?
That's just, I prime, yes, thank you.
Okay, yeah.
I prime, there we go. Okay, so let's, so based on the fact that I prime, we know the length of I prime is 1, let's compute the lengths of each side of the triangle. And so what we can do is we can say I prime is equal to cosine theta I plus sine theta j. And basically we're using vector addition rule here for that. Okay. So we're saying if we want to obtain the I prime vector, one way we can do is we can add a vector in the I direction and another vector in the j direction. Okay. Let's do the same thing for the j prime vector. And so j prime vector is going to go in that direction just like that. Okay. Let's go ahead and draw the triangle here. And so just like before, any line here that's going vertically up, we can say this is the same direction as j. And then this side of the triangle, this one's interesting because it's actually going to the left, right? We know that the default I vector points to the right. And so if we're going to the left here, that's going to be in the negative I direction. Okay. And so if we do the same vector addition and we use trigonometry, what we can say is that J prime is equal to minus sine theta I plus cosine theta J. Let's put these two relationships into a matrix form to form a system of equations. Okay. Okay. And so we have I prime is equal to cosine theta I plus sine theta J, and then J prime is equal to minus sine theta I plus cosine theta J. Okay. If we were to put this in kind of vector matrix form, we could say that I prime, J prime is equal to cosine theta, sine theta, and sine theta, cosine theta, divided by I and J. Okay. And so hopefully, from here you can see kind of what we've done. And so, based on those two kind of trigonometric vector relationships, we're able to form this kind of linear system, which has this transformation matrix that we need. Okay. And so this right here, this is the transformation matrix that will let you transform. It'll let you transform coordinates in the original coordinate system to the new rotated coordinate system. Okay. And so the way that you use it, we're going to do an example in a second. And so the way that you use it is you basically plug in coordinates in the original system. You plug it in for I and J. You multiply that by the transformation matrix, and you get the corresponding coordinates in the rotated coordinate system, the I prime, J prime. Okay. All right. So before we do kind of a quick example on that, are there any questions on this? Okay, all right, let's do an example so you can kind of see how this is used. Okay, and so let's say that our point P, let's say that has coordinates of 3, 2 in the original XY frame. Now let's say that we've taken that frame and we've rotated it 30 degrees counterclockwise into a new frame. Okay. Okay. And so let's use, well, first let's compute the transformation matrix for this for this rotated frame, and then let's compute what the coordinates are going to be in the new frame of that point P. Okay. Okay. All right, so let me go ahead and draw it first. And so let's say that we have a starting coordinate, and you don't always have to start. I mean, you don't. I mean, I know the example that we're doing. We're starting from the kind of normal XY coordinates, but you don't have to start from here. So you can kind of start from any orientation and rotate it as you want. And in fact, for motion tracking, that's usually the case because your coordinates, your anatomical coordinate systems are probably going to be pointing down the length of the bones, and so you're going to start with whatever orientation that is. Okay. But for this example, we'll start with just standard XY. All right. And so we've rotated 30 degrees. So we have a system that looks like this. Okay. We have our point P. And point P might be somewhere here. And the coordinates for point P are 3, 2. Okay, so it's X, its regular X coordinate is 3, its regular Y coordinate is 2. Okay. And so we want to see what the transformation matrix is between X and X prime, and what the coordinates of P are going to be in that new reference frame. Okay, first let's compute the transformation matrix. And so we know the angle of rotation. We know it's 30, and so R here is going to be cosine 30, sine 30, minus sine 30, and cosine 30. Okay. And so you plug that in, you punch all that into your calculator, you get √3 over 2, 1/2, minus 1/2, √3 over 2. Okay. Okay, so now let's compute the coordinates of P in the X prime, Y prime system. Okay. And so we know that the coordinates in X and Y are 3, 2. Okay. And then all we have to do is multiply it by a transformation matrix. So it's √3 over 2, 3. Okay, 1/2, minus 1/2, √3 over 2. Okay. And so all we have to do is just perform this arithmetic here. And so it's a little bit tedious because whenever you do matrix vector multiplication, but this gives us √3 or 3, √3 over 2 plus 1, and then minus 3 over 2 plus √3. So not pretty. And I when I was writing this example, I was like, oh, that's kind of an ugly answer, but it is what it is. And so when you have 30 degrees or 60 degrees, you're gonna have √3s in there, and √3s are not pretty numbers. All right, and so if you punch those into your calculator, you probably get kind of a decimal approximation. And so what you'll see is that decimal is going to be different from the 3, 2 that we had previously. Okay. All right, so that's the basics of transformation matrices. And so the idea is to get this matrix, and then we can use it to transform the coordinates or vectors as well between two different coordinate systems. Okay. All right, any questions on this? Okay. All right, so before we move on to 3D, I do want to let you know of one really nice property of transformation matrices is that if you want to find its inverse, then all you have to do is take the transpose. Okay? Right now, what we have is I prime j prime is equal to r times I j. Okay. Well, I would say this, one way we can define, or one way we can kind of improve our notation here is that instead of just saying R, we could say is that this is the R between X and yeah, so this is going to be the transformation from X prime to X, or X from X to X prime, sorry. Okay. And so what this means is that this transforms from the X coordinate system to X prime system. And so if we have this transformation matrix, we multiply it by coordinates in the X system, and we get coordinates in the X prime system. So we go from X in the bottom to X prime up top. All right, but sometimes maybe we want to go backwards. So, let's say that we want our X prime. And so if we multiply that by I prime, J prime, this is going to give us I and J. Okay. And so this is kind of the reverse transformation. So this goes from X prime system to the regular X system. All right, and these are different. And so the two R's that I have there are different matrices. So mathematically, they have different values. But luckily, these two are related. And so, basically, these two matrices, if you can kind of see that how they are located in a linear algebra way, these two matrices are inverses of each other, right? And so to get one, you just take the inverse and then you get the other one. Okay. And the nice thing about transformation matrices is that instead of having to take a matrix inverse is kind of a messy, kind of really involved process. These transformation matrices have a nice property where all you have to do is just take the transpose and you can get the opposite. Okay. And so what we can say is that X, way to get this is to just take the transpose and so if you've never seen this notation before, if you see a T kind of in the exponent there, all that means is just to take a transpose of that matrix. Okay. And so using that logic, what we can say is that X are X prime, okay, which remember is the transformation matrix that takes in coordinates from the prime reference frame and spits out coordinates in the original reference frame X. This value, all I'm going to do is I'm going to take this system here and just transpose it. And so it's going to be cosine theta, sine theta, minus sine theta, cosine. So all that is just the transpose of the original transformation. Okay. And this property is going to hold in three dimensions as well. So in 3 dimensions, this is this works just fine. Okay. Okay. All right. So that's a nice property, and that's going to help us out moving forward. So let's talk about how we do transformations in 3D. And I apologize. I don't think I'm going to get to the example today. But homework 5 is just going to be posted tonight. So we're going to have a few weeks to do it anyway. So we'll definitely do the example on Tuesday. But let's talk about how we do 3D transformations. Right. And so remember, when I first started off our discussion on transformation matrices in 2D, I said that in 2D you only need just one rotation, right? So that's kind of the only thing that you can do. In 3 dimensions, because we have that extra kind of dimension here, that means the amount of rotations that we can actually make are 3. Okay? And so it's not like a 2D case where you can only just rotate around. Just, well, in 2D, the z-axis is kind of implied to be coming out of the page. And so when we're making a rotation in 2D, we're just rotating about that z-axis. But in 3 dimensions, you have perspective. You have three coordinate axes, and you have perspective in each direction. That means you can rotate around each of those coordinate axes. Okay? Okay. All right, and so as you can imagine, if you do 3 rotations, this kind of complicates our situation considerably, because we have to kind of track 3 rotations throughout the entire motion. Okay, and once you start thinking about kind of coordinate transformations in 3D, and even I still struggle with this. It's really hard to visualize. And so what I'm going to do is, I'm going to use an analogy of an airplane, because I think that's going to help with this. Okay, and so even if you have kind of the most basic knowledge of how an airplane works, you've probably heard of the terms called pitch, roll, and yaw, right? And so those are terms that that kind of describe how a plane is oriented in 3D space. And so we're going to use those kind of that kind of analogy. And if you don't know what those are, don't worry about it. I just kind of learned somewhat recently within the last couple of years too, even though I've heard those terms for a long time. And so I'll draw a lot of pictures and we'll talk about it just so that you can kind of see. Because I think this is kind of the hardest part here to visualize. Okay. And so the nice thing about transformation matrices in 3D and transformations in general is that you don't have to do all 3 rotations at the same time. And so what you can do is you can think of a 3D transformation as 3 sequential rotations in 3 different directions. Okay? Okay, and so we're gonna use that knowledge, the fact that we can take these rotations sequentially together with our airplane analogy to kind of make things a bit better. Okay. Okay. And so kind of the scene that I want you to visualize is, let's say that you're sitting on a commercial airplane and it's sitting on the tracks. Okay. So this is before takeoff. And so in order to get the plane into the air, the plane is going to have to undergo a series of maneuvers in order to, point its direction in the, in order to orient itself to basically, first of all, take off, and then to also kind of point it towards whatever your destination is. Okay. And so let's imagine okay. All right, so let me go ahead and try to draw an airplane. For some reason, the most detailed part of this airplane in my notes is the tail. Okay. All right, so there is your airplane, or kind of a cartoon rendition of an airplane. Okay. All right, and so let me go ahead and define the coordinate axis. And so, we're just like we did in 2D, we're going to start with, I would say, kind of a starting coordinate system or starting reference frame. And then from that, we're going to rotate into our real one. Okay. All right, so let's imagine that the x-axis is pointing down the barrel of the airplane. Okay. We'll assume the y-axis is pointing down the wing. And then we'll assume the z-axis is pointed straight towards the ground. And so that's going to be our starting coordinate system. And what this represents, kind of our starting point, is going to be the plane that's on the ground, trying to get onto the runway. Okay. Okay. So that's what it represents. So you're sitting on the plane, you just boarded, you just texted your friends, hey, I'm on the plane, you turn on to airplane mode, or maybe you're a rebel, maybe you don't turn on airplane mode, but you're sitting in the seat and you're just waiting for it to take off. Okay. And so in order to get into the air, the plane is going to have to do a series of maneuvers in order to get there. Okay. And so let's define those maneuvers in terms of rotations. And so let's say we're going to have a rotation around the z-axis. Okay. So we'll call that rotation theta. Okay. Okay, then we're going to have a rotation about the y-axis. We'll call that rotation phi. And then finally, we'll have a rotation around the x-axis. We'll call that psi. Okay. So theta, rotation around the z-axis. Phi, the rotation y-axis. And psi, this is rotation axis. Okay. Okay. All right, and so we're going to perform all three of these rotations, and we're going to do them in sequence. Okay. Okay, so that's kind of the analogy that we're going to be working with here. Are there any questions on this? Okay. All right, so let's start rotating. And so, the first thing we're going to do, and so the first thing a plane does kind of when it's on the ground is that, let's say you're taxiing, and then you're trying to get on the runway, and then the plane has to kind of turn while it's on the ground in order to get onto the runway. Okay. And so which of the angles that we have here would kind of represent a turn that's on the ground? It would be theta, right? So it would be a turn around the z-axis. So the z-axis is pointing downwards. And so if we're taxiing and we're kind of turning just on the ground, then that rotation would be characterized by theta. Okay. So let's take that information and let's form a transformation matrix for this rotation. Okay. And so that transformation matrix, now we have a 3 by 3, by the way, because we're in three dimensions here. our transformation matrices are also going to be 3 by 3. Okay, because we have to transform 3 coordinates into another 3 coordinates. So that's to be 3 by 3. Okay. And so the convention that we use is this. And so we know that the theta here is a rotation about the z-axis. Okay. And so whatever axis we're rotating around, we're going to make that row and column zeros. Okay. And so if we use the convention of x, y, z, we're going to start our transformation matrix like this. Okay. And so we're going to put zeros in the z row and in the z column, okay, for the x and y rows and columns, but we're going to put a 1 on the diagonal. Okay. All right. And so for the x and y columns, what we're going to do is we're going to input our 2D transformation matrix that we derived earlier. Okay. And so even though we're in 3 dimensions, the rotation that we're doing, we're only kind of changing coordinates in just two of those dimensions. Okay. So the third one is fixed. And so what we can do is we can say that this is going to be cosine theta minus sine theta, sine theta, and cosine theta. Okay. And so those sines and cosines come from the 2D transformation matrix. Okay. In particular, it came from the second one that we went over, which was a transformation from the new coordinate system, from the rotated one to the old one. And so if I were to define this transformation matrix, it would look something like this. Okay. And so notice the convention here. And so, oh, by the way, I put lab there. And so lab is, it's a lot shorter to write than our starting coordinate system or our start. And so the lab coordinate system is just to refer to any kind of fixed coordinate system on the ground. So that can be like our starting coordinate system. Okay. So this lab R1, this is the transformation matrix from the rotated coordinates to the starting coordinates. Okay. Excuse me. Okay. All right, and so all we did basically was just use our 2D transformation matrix here, and then we kind of combined it in 3. So this is kind of our first maneuver. All right, any questions on this so far? Okay. All right, so that's our first maneuver. And so we need to do 2 more before we can kind of start heading towards our destination. Okay. Okay, so for the second maneuver, let's say that we're on the runway and as the plane starts to accelerate. And so in order to get off the ground, what we do is that we kind of tilt upwards, right? So we kind of tip the nose upwards, and we hope to God that aerodynamics still exists, and then we're able to take off from the ground. Okay. And so if we look back at our original figure here, okay, and so if we were to tip the nose upwards, the way that we would do that is by rotating around y-axis, correct. And so the angle that's going to characterize this is the phi angle. Okay. All right. And so I'm going to go a bit faster here just because I want to make sure I get to a certain point before we go. Okay. And so if we know that we're rotating around the y-axis, then we can write the transformation matrix. Okay. And so after the second maneuver, I'm going to say that we're going to be in configuration 2. Okay. And so the transformation matrix from 2 back to configuration 1, which is what we had in the last step, is given by a rotation in the y-axis. Okay? So if we're rotating around the y-axis, our transformation matrix will look like this. Okay. We're going to have cosine phi, sine phi, minus sine phi, cosine phi. Okay. If you'll notice in this transformation matrix, the minus sign is in the other location here. Okay. And that kind of has to do, that kind of more has to do with how we define the coordinate system. And so I would say for a lot of the times, you're not going to be computing the transformation matrix like this. And so you don't have to worry too much about where the negative is. But if you're kind of curious about why the negative is here, you kind of have to go back to the original geometry and kind of rotate and see kind of what's going on. And so it's kind of due to the fact that, you know, our z-axis is pointing down and our x-axis is pointing to the right. I can get into more next time if you're curious. Okay. And so in the third maneuver, the last one we have to do here is, you know, let's say that we're in the air, but our plane is not facing in the right direction. So let's say that we're taking a plane to San Francisco, but our plane, you know, maybe it's pointed towards Vegas or something. Okay. Vegas is fun, you know, but we have an engagement to get to in San Francisco. And so what we need to do is the plane needs to kind of, you know, turn in midair in order to point its nose in the right direction. Okay. And by process of elimination, you can probably guess that this is going to be a rotation around the x-axis, which is characterized by the psi angle. So our transformation matrix, we'll call it 2R3 is equal to 1, 0, 0, then 0, 0, cosine psi, minus sine psi, sine psi, cosine psi. Okay. All right, so that's our third transformation matrix. Okay. So now we have 3 transformation matrices that characterize all 3 of our maneuvers here. And so our last step here is going to be to combine these 3. Okay. And so, you know, we are out of time, and so I don't want to spend any much longer on this. But I'll tell you that on Tuesday, you know, all we have to do here is we take these 3 transformation matrices and we just multiply them by each other. And so if you multiply them by each other, then you get a single transformation matrix here that captures all 3 maneuvers. Okay. But we'll get into that on Tuesday because it takes a bit of complexity to write that. All right, any final questions before we wrap it up for today? Okay, all right, so we'll wrap this up. We'll pick this up again on Tuesday. So remember, homework 4 is due tonight. If you have any questions, you know, I'll try to be on my email tonight, so you can email me. But other than that, hope you guys have a great weekend, and I'll see you guys on Tuesday.
Question 4A part 3.
Yeah.
I feel like I got the process right. So it's asking for the amount of fibers. Do you remember that one?
Yeah.
So I converted the area for 2 meters just for me, and then I have the area from the previous part. But I'm getting a number that's not, it doesn't match. I'm off by 300. It's
Oh, okay, I think,
12,
yeah, I think what I did there is I just rounded, because it's, I think it's like 128, and I just rounded down to, 125 or something.
I just want to make sure whether I'm doing something wrong or
Yeah,
those are my issue.
So like 70.
Let me see.
Part 3. So this is the main calculation.
Right.
It's 12.8. And then I got
So for this,
from the radius of the muscle fiber, so 100. Well, I did 100 because I wanted to do in diameter.
okay, so 100 divided by 4 squared multiplied by 5, right? That gives you -9.
Yeah.
Wait, okay, so if it'd be 50 micron radius, so the area would be 2,500 micrometer squared. And so if we convert that to meters, this would be 2,500 pi, the 2,500 times pi is about 8. It's about 8. Okay. Yeah, it might just be a rounding thing, because I think I might have rounded that. I might have had some additional sig fix to that, and so that ended up being 120. I think that's what it is.
I
But you're
have
definitely on
it
the
here
right track.
too. This one you're using the number of
Yeah.
micrometers. If
Right.
you use this number, this is completely off. But if you use the actual number,
Yeah.
it aligns with the given answer.
I see.
Which is why was it a rounding issue? Or
Yeah, those are just because these numbers are so big. I think they're
Right.
just rounded off, so yeah, as long as you're pretty close on that.
I just wanted.
For sure, for sure.
For me, I guess.
I got
a question on 2C.
Okay.
I was actually.
Or I can go over there.
So, I was looking at, one of the recordings I talked about is essentially. In the video, you were saying, following this equation, and then I will give you the balance has to spend down. So we give you 0.6, and then I will do that.
I did myself. I would double check this.
Oh,
2,100 meters divided by 15 minutes. That's 100 seconds. I think this is like 2.7.
So what changes this?
No.
But then when you get this, is it going to be like, this is like, you know, I get the point. Okay.
So this problem was interesting. So I had a couple more. That's why I asked the rest of the problem. But I realized the rest of the homework. I left. Yeah. I know it's kind of throwing everyone off, but I had other stuff going pretty strong, but it didn't make the final cut. So that's why I left it in there.
For this one, is this one round 4 is to here, right?
Exactly.
Is it basically like this trough is supposed to be?
Well, so this is actually going to be. This is actually supposed to be for the entire warm side.
Yeah,
And so obviously it doesn't have to shape, right? But the reason for that is because it's kind of.
Oh, so it's instead of just one time zone.
Exactly. So you're gonna get a curve that's very good. So kind of the.
Yes,
Pendulum, you can get some, something out of my graph, so it's not gonna get as good.
Okay. So for this one, the last so run last year. So for the homework, for the second one, you had to do the area.
It was like this.
You want us to.
Yeah, like this plateau.
Oh, you don't have to.
Yeah,
So
so
when I said the value, I needed.
Oh, yeah, to get the bounce. I put plateau.
Right. So for the short muscle.
Right.
That has 10 muscles together, that's gonna be.
Right.
So some people actually do this, so they use the.
Number bonus.
And I was something on the wax and whack.
But you don't have to, so I'll.
Wait, is it fine? I just wanted to start to write.
Stress, strain.
That essentially.
Yeah. I was like, so the main difference is that now this one.
I got mine.
Yeah, but you can't.
Exactly.
Right.
So
Oh,
this
yeah,
one-
it's just like negative 4.
Or this one should be 10 times higher.
Oh.
Because this is the parallel.
Right.
But this one's also 10 times wider. So this section is, it's hard to tell.
Yeah.
But if you kind of line these up, this would be 10 times longer.
Oh.
And so that's the trade-off. So you have a parallel muscle, you get more force, but you're operating within a longer range. But for the longer muscle, you get less force.
And for the last question, do we have to use the formula where the fast twitch muscle, fast, slow twitch, and quick twitch, it says.
No. So if you look back, I think it's in the same section of notes where I have.
It's not gates.
Actually, no.
This
good. Yeah, so that's.
And so if you go to the section where I talk about.
Yeah, that was where you mentioned slide time.
Yeah.
Yeah, oh,
And so for a longer muscle.
you think so? Is that Marble Street?
Yeah, so basically,
You don't
these two questions, right, these two.
Oh.
And so for a thin muscle, that's maybe longer, you're gonna get a force on the curve that's shifted to the right, so it's wider. But for a thicker muscle, it's gonna be higher.
Like you said,
And then for the force velocity curve, it's gonna look like this. For a thicker muscle, you produce a higher force, but it kind of like for the thinner muscle, the longer muscle, it powers less force.
Yeah.
I think the maximum, but it higher.
So the thinner one is the
Of the force.
Alright.
Yeah. Yes. Which animal? Oh, okay, yeah, no, that'd be great. Usually we only do one, but you guys want to do all five.
Oh, we have an option to do only one?
Yeah.
But we'd have to do like five different motions.
Yeah, so 5 different. So I'll leave it up to you. Yeah.
Let's see.
You guys have 2 more people.
Yeah, one more.
Okay, try to get a group of 4 just because we have 40 something people in the class, so I want to make sure we have. If you guys can't find a board one, then we'll probably strive with it, so. So, if you can find one, great, but if not.
Be aggressive.
Yeah.
So it's kind of like moving to 410.
Yeah.
I was wondering why I was getting this error. It's not all minutes. I don't know what it is. And, yeah, I googled it and they were saying like my naming conventions were wrong. I didn't.
But you haven't named it.
I never named anything
Yeah.
besides I guess like the materials.
Yeah.
But that's just like sliding it over.
So it's really weird.
But it runs smoothly, so I have absolutely no idea. So I don't know if that will like. affect-
Just a warning?
Yeah, it's just like a warning, like,
Okay.
I'm still getting like this, like.
Let me see this information stuff. That looks okay. That looks fine. Can I see the stress?
Yeah.
I think it's fine.
I'm still trying.
Okay, I'm not sure why it's given, but I wouldn't, because Ansys has this feature where you can like click on certain surfaces and then give them a name. So that if it's like a surface you're gonna apply by boundary conditions on later, you can kind of refer to it. But I haven't taught you guys how to do that, and so I didn't think anyone's gonna do it. And so I don't know if that's like an artifact from how the car was made or something like that, right? Don't worry.
Okay,
I think it's fine.
all right, I'll just leave that. Thank you.
Yeah.
I wanted to, so I ran all 3 conditions for, I did the turbine fin, and I wanted to kind of like run them past you and see if they all like make sense.
Okay, yeah.
So for one of them, I fixed the like rectangular part of the turbine, of like the non-fin part.
Yeah.
Just called it fixed. Yep. And then I imagined it being in like a vehicle's turbocharger.
Yeah.
And some values from the internet and looked up rotational forces and ended up finding like it could be experiencing like 6,000 newtons of force at the tip of the fin.
Yeah.
And I just called that just like a pulling, since it's spinning, I figured like some type of force, whatever,
Yeah.
I'd be pulling it outward. I just called that like fixed point and then rotational, like that causes the perfect straight force.
Yep.
And I did that with two different materials. So one material, and then I just same exact test, but with another material. That kind of two different.
Yeah.
And then the last one I did was I was predicting it to not be spinning, but instead to be just like fixed. Once again, like in a car, the car is going like 120 miles per hour. And so it's not rotating, but it's experiencing like a front load from like wind force at 120 miles per hour. And then also due to the shape of it, I did like took some leniency here and did some like estimation on lift forces for the shape of it.
Sure.
And so that has like front force right on the front of the fin, and then also a certain amount of lift force.
Yeah.
And I went back to like the original material to see how that worked, because that counts as 3, and we just
Perfect.
write it all up and justify everything.
Perfect.
Okay, awesome, thank you.
Yep. Almost 5:30.